Distance between two parallel lines. Welcome, everyone. Today, we are going to explore a fundamental concept in three-dimensional geometry, finding the distance between two parallel lines. Before we dive into the complex formulas, let's start with the basics of what actually makes two lines parallel in a 3D space. First, it is important to understand that parallel lines must be coplanar, which simply means they lie within the same flat plane. Even though we are working in 3 dimensions, these lines will never intersect, no matter how far they extend. Secondly, the key characteristic that defines them is their direction. Parallel lines move in exactly the same direction, which mathematically implies that they share the same direction vector. As we move through the next few slides, we will see how we use this shared direction vector to mathematically represent these lines and ultimately calculate the shortest gap between them. Understanding the mathematical representation. Now that we have established what parallel lines are in 3-dimensional space, let's look at how we actually represent them mathematically using vectors. When we are dealing with two parallel lines, their vector equations follow a very specific structure. For the first line, which we'll call L1, the equation is written as r equals a 1 plus lambda times b. For the second line, L2, the equation is r equals a 2 plus mu times b. Now, I want you to pay close attention to the vector b. Notice that it is exactly the same in both equations. This is the most important part, as it represents the common direction vector that we mentioned in the previous slide. To break this down further, let's define our components. The vector A1 is the position vector of a specific point. Let's call it point S, located on our first line. Similarly, the vector A2 is the position vector of a point, which we'll call point T on our second line. Finally, you'll see the Greek letters lambda and mu. These are simply scalar parameters. They allow us to move along the lines, and as we will see in the upcoming slides, the distance between these lines depends on how we use these vectors to find the perpendicular gap between point S and point T. The concept of distance. Now that we have established the mathematical notation for our two parallel lines in the previous slide, let's dive into the actual concept of distance. First, it is important to understand what we mean when we talk about the distance between these lines. Because these lines are parallel, they never get closer or further apart. Therefore, the distance is defined as the constant perpendicular distance between them. To visualize how we calculate this, imagine picking any arbitrary point, let's call it point T, located on line 2. To find the distance, we want to find the exact length of a perpendicular line segment dropped from that point T straight down onto line 1. To do this mathematically, let's look at the points we identified earlier. If we draw a vector connecting point S on line 1 to point T on line 2, we create the vector SD. In terms of our position vectors, this vector SD is equal to a 2 minus a 1. Now, here is the key insight. The vector we just created, SD, might be diagonal, meaning it's not necessarily the shortest path. The shortest distance, which we will call D, is specifically the component of this vector SD that is perpendicular to our common direction vector, B. In the next slide, we will see how we use the cross product to isolate this perpendicular component and arrive at our final formula. Formula for shortest distance. Now that we understand the geometric concept of dropping a perpendicular from one line to another, let's translate that idea into a concrete mathematical formula. By utilizing the properties of the vector cross product, we can derive a precise way to calculate this shortest distance. The magnitude of the distance, which we'll call D, is given by the absolute value of the cross product of the common direction vector B and the vector difference, a sub 2 minus a sub 1, all divided by the magnitude of the direction vector B. Essentially, this formula allows us to find that perpendicular height we discussed in the previous slide using only the components provided in the line equations. In the next few slides, I will show you exactly how to apply this formula step by step to a real-world problem. Step-by-step procedural application. Now that we have seen the theoretical formula on the previous slide, let's break it down into a practical, step-by-step procedure. If you follow these 5 manageable steps, you will be able to solve any problem of this type with confidence. Step 1. First, you need to identify your components. Look closely at the given vector equations of your lines and extract 3 key pieces of information. The position vector of the first line, which we call a 1, the position vector of the second line, a 2, and the common direction vector, which we'll call B step 1. Identify the components, extract the position vectors backslash vec1 backslash, and backslash vec2 backslash, and the common direction vector backslash vec b backslash from the given equations of the lines. Step 2. Next, we need to find the vector difference. We want to find a vector that connects a point on the first line to a point on the second line. To do this, simply subtract the first position vector from the second. We can represent this new vector, v, as a 2 minus a 1. Step 3. Step 3 involves a bit of vector algebra, computing the cross product. You will take that common direction vector, b, and find its cross product with the difference vector we just calculated. We can call this resulting vector w, where w equals b cross a 2 minus a 1. Step 4. Once you have that cross product, you need to find the magnitudes. This means calculating the length of our new vector, the magnitude of w, and also finding the magnitude of our original direction vector, b. Step 5. Finally, we reach the final calculation. To find the actual shortest distance, d, simply divide the magnitude of the cross product by the magnitude of the direction vector. If you follow this sequence, you'll see how we arrive at the final result, which we will demonstrate in the upcoming real-world example. Real-world example. Now that we have understood the theory and the formula, let's put everything we've learned into practice with a real-world application. Imagine you are looking at a landscape where 2 high-voltage power lines are running parallel to each other across the terrain. To solve a problem like this mathematically, we represent these lines using a coordinate system. Take a look at the equations provided. The first line, L1, is represented by the vector equation r equals I plus j, plus lambda times the quantity I plus 2j plus k. The second line, L2, is represented by the vector equation r equals 2I plus 3j, plus mu times the quantity I plus 2j plus k. Notice something important here. Both lines share the exact same direction vector, which is I plus 2j plus k. This confirms what we discussed in the earlier slides, that these lines are indeed parallel. Our specific goal for this exercise is to apply the formula we just learned to find the shortest distance between these 2 power lines. In the next slide, we will walk through the calculation step by step. Step-by-step solution. Now that we have our scenario involving the power lines, let's walk through the actual calculation step by step to find that shortest distance. Starting with step 1, we need to identify our components from the equations we saw on the previous slide. We'll extract the position vector a1, which is I hat plus j hat, the position vector a2, which is 2I hat plus 3j hat, and our common direction vector, b, which is I hat plus 2j hat plus k hat. Moving to step 2, we need to find the vector connecting these 2 points. We do this by calculating a 2 minus a 1. When we subtract I hat plus j hat from 2I hat plus 3j hat, we are left with a difference vector of I hat plus 2j hat. Next, in step 3, we perform the most critical part, computing the cross product of our direction vector b and this difference vector we just found. To solve this, we set up a 3x3 determinant using the unit vectors I hat, j hat, and k hat in the first row, followed by the components of vector b, and then the components of our difference vector. Expanding this determinant along the top row, we calculate the I hat component by taking 2 times 0 minus 1 times 2, which gives us negative 2 I hat. For the j hat component, we take negative the quantity of 1 times 0 minus 1 times 1, which simplifies to plus 1 j hat. Finally, for the k hat component, we take 1 times 2 minus 2 times 1, which results in 0. So, our resulting cross product vector is negative 2 I hat plus j hat. Now, in step 4, we need to find the magnitudes of the vectors we've worked with. First, we find the magnitude of that cross-product vector we just calculated. Taking the square root of -2 squared plus 1 squared plus 0 squared, we get the square root of 5. Next, we find the magnitude of our original direction vector b taking the square root of 1 squared plus 2 squared plus 1 squared, we get the square root of 6. Finally, in step 5, we apply our formula from the earlier slides. We divide the magnitude of the cross product by the magnitude of the direction vector. This gives us a final distance, d, of the square root of 5 over the square root of 6 units. As we move to the next slide, keep this calculation in mind, as I will highlight some common pitfalls students encounter when performing these exact steps. Common mistakes to avoid. First, a very important one: avoid using the formula for skew lines. You might remember from previous lessons a formula involving the dot product of the cross product of two different direction vectors, divided by the magnitude of that cross product. Please do not use this here. Because our lines are parallel, their direction vectors are the same, which means their cross product is 0. If you try to use that formula, you'll end up trying to divide by 0, making the calculation undefined. Always verify that the lines are parallel before you begin. Second, watch your denominator. A frequent mistake I see is students successfully calculating the magnitude of the cross product, but then forgetting the final step. Dividing by the magnitude of the direction vector, b. Remember, the distance is the height of the parallelogram, so you must divide by the base length. Finally, be extremely careful with sign errors during vector subtraction. When you are finding the vector a 2 minus a 1, a single misplaced minus sign will propagate through your cross product and your final magnitude, leading to an incorrect answer. Take your time with the arithmetic in those early steps. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even when you understand the concept, it is very easy to make a computational or conceptual error. If you can avoid these 3 traps, you'll be well on your way to mastering this topic. Key takeaways. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. First, let's revisit the condition for parallelism. Remember, before you even begin applying the distance formula, you must verify that the lines are actually parallel. You can do this by checking their direction vectors. If the vectors are identical, or even if one is just a scalar multiple of the other, then you know the lines are moving in the same direction and are parallel. Next, let's think about the geometric meaning of what we are calculating. When we talk about the distance between these two lines, we aren't just looking at any random gap. We are specifically looking for the length of that one, unique, perpendicular segment that connects the two lines at a right angle. Now, let's look at the formula one more time to ensure it's etched in your memory. The distance, d, is equal to the magnitude of the vector cross product of b and the vector a sub 2 minus a sub 1, all divided by the magnitude of b. Finally, I want to leave you with a deeper intuition regarding the core operation of this formula. Think about the cross product of b and the vector a sub 2 minus a sub 1. The magnitude of this cross product actually represents the area of a parallelogram formed by the direction vector b and the vector connecting our 2 points. When we divide that area by the magnitude of the base, which is the magnitude of b, what are we left with? We are left with the height of that parallelogram. In our context, that height is exactly the shortest perpendicular distance between the two lines. I hope this breakdown helps clarify the concept. Keep practicing, and I will see you in the next lesson.